Hello, and welcome to our first lecture on trigonometry. In the next large block of lectures, we're going to study angle measure, the trigonometric functions, their graphs, equations involving trigonometric functions, inverse trigonometric functions, all kinds of identities involving trigonometric functions, and of course, throughout this, a lot of applications of trigonometry. Needless to say, this is a crucial topic in applied mathematics, engineering, and especially calculus. One has to be very strong in trigonometry to be successful in calculus. And loosely speaking, trigonometry models periodic behavior like wave motion, but it does more than that, it turns out. Let me give you some history of trigonometry. It seems that the word trigonometry comes from a Greek word that means measurement of angles. And initially, trigonometry dealt with relationships between sides and angles of triangles. And it was used by surveyors and astronomers and navigation to locate positions on the ocean and things like that. But then in the 1600s, when calculus was being developed, scientists discovered that trigonometry was a lot more. In fact, there were trigonometric functions, and these functions formed a new class of functions, much like the polynomial functions and logarithmic functions that we've been talking about in the past. And the focus of this block of lectures will be these trigonometric functions. And we'll see that they have lots and lots of applications to sound waves, vibrations, light rays, orbits of planets, pendulums, etc. Now, I'd like to, before approaching trigonometry and defining the trigonometric functions, I'd like to spend this lecture on angles. How do you measure angles? Because we'll need to use angles when we define the trigonometric functions. And it turns out there are basically two important ways of measuring angles: degree measure or radian measure. So I'd like to first look at degree measure, and then in a few minutes we'll go over to radian measure. But first, what's an angle? Let's give a formal definition. An angle is determined by rotating a ray, and you rotate it about its endpoint. And the starting position of the ray is called the initial side, and the end position is called the terminal side. And the endpoint of the ray is, of course, the vertex. Here's a picture of a typical ray, and notice how the initial side has rotated over to the terminal side. Now, if this angle is positioned such that the vertex is at the origin, and the initial side is on the positive x-axis, we say that the angle is in standard position. So here's an example of an angle in standard position. And if it's counterclockwise motion, then we say it's a positive angle. So counterclockwise rotation from the initial side to the terminal side, that's a positive angle, and the opposite direction is a negative angle. Here's some examples of those two things. Here's a positive angle starting at the x-axis and rotating over, and then the negative angle would rotate clockwise. All right, good. I think we're pretty familiar with angles. Usually we denote angles by Greek letters. That said, you can use any kind of notation you want, but you'll see a lot in textbooks that they use Greek letters like alpha, beta, gamma for angles. And also, if two angles, you might have an angle that rotates back to itself, and those are called coterminal angles. Here are a couple of pictures of coterminal angles. The angle alpha here is a positive angle, and it's rotated over there to what we call the third quadrant. That's the quadrant where x and y are both negative. And then that's coterminal with the angle beta, which is a clockwise, so it's a negative angle. And they're coterminal because they finish at the same place. And then we have another picture here of two coterminal angles, alpha and beta again. Okay, so coterminal angle, and they'll come up quite a bit. So what's 1 degree? What is degree measure? Well, The way they do this, and you're probably familiar with this, the full circle is 360 degrees. So 1 degree is 1/360th of a complete revolution about the vertex. That's what 1 degree is. And here's a picture of a circle with a lot of degree markings. Let's sort of savor this for a moment. You see over there 0 degrees. There's essentially no angle at all. And then I see 90 degrees. That's a perpendicular. That's perpendicular line to the x-axis. That's a 90-degree angle. 180 is over on the other side. You see 270 down at the bottom, and then finally you get back to the coterminal angle with 0, and that angle would be 360 degrees, wouldn't it? And in the picture, I think we've indicated a 45-degree angle. And you see a 30-degree angle marked a little bit lower than the 45, etc. So these are some common angles that we'll use over and over again as we progress through our trigonometry. Let me remind you of some definitions from your geometry background. You probably remember that an acute angle is an angle between 0 and 90 degrees. A right angle, as I said earlier, is 90 degrees. What's an obtuse angle? Well, that's an angle that measures between 90 and 180. And then you have what's called a straight angle, and that's 180 degrees, a half revolution around the circle. A full revolution is 360 degrees. And as I said earlier, 0 degrees and 360 degrees are coterminal angles. How do you measure angles? What do engineers or geographers do to measure angles? Well, they use a protractor, or at least they used to. And protractors are little plastic devices that measure angles, usually in degree measure. Here's another picture we might want to look at for a moment. Here I've talked about acute angles and obtuse angles, etc., in terms of the quadrants. You might remember that the coordinate system, the XY coordinate system, can be divided into 4 quadrants. And in the upper right corner is the first quadrant. That's where X and Y are both positive. And in that quadrant, angles are between 0 and 90 degrees. And you can go around that way. In the second quadrant, angles are between 90 and 180 degrees, etc., etc. So it's kind of nice to see the quadrants and the corresponding angles in those quadrants. All right, let's do some examples. We talked about coterminal angles. Let's try to find 2 coterminal angles with the angle theta equals minus 120 degrees. So let's find 2 coterminal angles, say one positive and one negative, for the angle theta equals minus 120. And then I'll show you a picture. Well, all you have to do is add 360 or subtract 360. If you add 360, one more trip around the circle, you get 240 degrees. And if you subtract 360, you get minus 480 degrees. Those are coterminal angles with minus 120 degrees. Here's a picture. I've drawn minus 120 degrees, and then I've also drawn the coterminal angle 240 degrees, which is a positive angle. Excellent. Okay. Here's another set of definitions you probably remember, but I'll remind you. We say that 2 positive angles are complementary, or complements of each other, if their sum is 90 degrees. And we say they're supplementary, or supplements of each other, if their sum is 180 degrees. Let me show you some quick examples. Given the angle 72 degrees, what's its complement and what's its supplement? Well, 90 minus 72 is 18, so 18 degrees is the complement because 18 plus 72 is 90. And subtracting 180 minus 72, you get 108 degrees, and that's the supplement. Okay, so that's pretty easy. Just by the way, a little fairly trivial pitfall. Angles greater than 90 degrees don't have complements. Of course not, because the sum has to be 90 degrees. For instance, 170 degrees does not have a complement, but it does have a supplement, 10 degrees. All right, good. On to radian measure. This is the way to measure angles in calculus courses. and in fact in most of science and engineering. Degrees are used a little bit, but in order to do a problem with calculus, you often have to convert your angle from degrees to this other measurement called radians. So let me talk about radians, let me define it for you, and then we'll show how you can go back and forth. But trust me, radian measure is more important. And unfortunately, it's perhaps not as, we aren't as comfortable with it if we've never seen it before. So how does radian measure work? Well, consider a circle of radius 1. And on that circle, draw an arc of length 1. So an arc of the circle of length 1. That cuts off an angle theta. And that angle theta is 1 radian. So 1 radian is the measure of a central angle that intercepts this unit circle in an arc of length 1. Okay? The radius of the circle is 1, the length of the arc is also 1, and the angle that is cut off there is, or subtends we sometimes say, is 1 radian. And it turns out a radian is about 57 degrees. I'll show you in a moment what the exact value is. It's about 57 degrees. Okay, so if you're given an angle in degrees, you may have to convert it to radians, or vice versa. How do you do it? Well, let me show you. This unit circle has a circumference of 2 pi. So 2 pi, that distance 2 pi, corresponds to 360 degrees, doesn't it? A full trip around the circle. So pi radians is 180 degrees. That's the fundamental comparison, the fundamental conversion formula for radians and degrees. Pi radians equals 180 degrees. In particular, 1 radian is 180 divided by pi degrees. And if you punch that in on your calculator, and by the way, your calculator has a button for pi, it's built into the calculator, you get about 57.3 degrees, as we saw earlier. And conversely, 1 degree would be exactly pi over 180 radians, which is about 0.017 radians. Not very big, not many radians. 1 degree is pretty small. Okay, so what are the conversion formulas? If you want to convert from degrees to radians, multiply by pi over 180. And conversely, if you want to convert from radians to degrees, multiply by 180 over pi. Let's do some quick examples. 90 degrees, a right angle. How many radians is 90 degrees? Well, you would write it as follows. 90 degrees, and then the conversion factor is pi radians divided by 180 degrees. And a little trick that I like to do, I like to put the units there. And then I see the cancellation of the units. The word degree cancels, and you're left with pi over 2. 90 over 180 is a half. So pi over 2 radians. So a 90-degree angle, a perpendicular, is 90 degrees or pi over 2 radians. Let's go backwards. How about minus 7 pi over 6 radians? How many degrees is that? Well, I think you see the picture. The conversion factor is 180 divided by pi, and if you put the units in there, you see again this very pleasant cancellation. The word radian cancels, and you're left with, well, the pi's cancel each other, the numerator and denominator. 180 over 6 is 30, and 7 times 30 is 210, and there's a minus sign out in front. So a lot of arithmetic, but you get the final answer of minus 210 degrees. Great, we're now experts in converting back and forth between these two units of measure. Warning, big warning. Perhaps the most common error I see when I teach mathematics. If you're using a calculator, make sure you're in the correct mode. All calculators have a degree mode and a radian mode. And if you're working with degrees, you better be in the degree mode. And when you're working with radians, be in the radian mode. I tell my calculus students, the first day of class, turn your calculator to radian mode, because in calculus, that's the mode you'll always use. And some of them never listen to me, and then they make mistakes on tests because they're in degree mode when the problem should be in radian mode. Okay, good. I hope we're sort of comfortable with these two ways of measuring angles. I want to take a moment now to talk about arc length of a circle and derive a formula that'll play a role later on in this course. It's the way to measure the length of arc of a circle. So here's the setup. Consider a circle of radius r. So here's a picture of a circle of radius r. And suppose the angle theta corresponds to the arc length s. So as I said earlier, it subtends or cuts off an arc of length s. How big is s? What's the length s? Well, we can derive a formula in terms of that angle and the radius. And this will be as follows in radian measure. The full circle is 2 pi r, but we're measuring a proportional angle of theta over 2 pi. So we have to multiply by theta over 2 pi. And now we have lots of pleasant cancellation, and we're left with r theta. So here's your fundamental formula. The length of that arc of the circle is r times theta. Let me savor that for a moment. R times theta. So imagine a circle. Here's a circle. What makes a piece of arc big? Well, there are two things that could make it big. One is the circle could have a big radius, and then it would have a big arc. Or the angle that you're subtending, that cutting off, could be a big angle, and that would also make it a big arc. So both r and theta play a role in calculating that length of the piece of the circle. Okay, so it's kind of a nice formula. Let me make one more comment about radian measure. Sometimes you'll see an expression like theta equals 2, theta equals 5, theta equals pi. Expressions like that, when there are no units mentioned at all, we understand that to be radians. Let me say it a different way. If you're using degrees, please say the word degrees. 12 degrees, 17 degrees. But if you just tell me 12, then I'm going to assume you're doing it in radians. And that's sort of the way it is. Okay, good. Let's do an example of our new formula for measuring arc length. And let's say the following setup. We have a circle of radius 4, and we have an angle that's 240 degrees. So here's a picture of the setup. The radius of the circle is 4, and it's a big angle. It's 240 degree angle. What's the length of that piece of circle subtended, cut off by that large angle of 240 degrees? That's the question. How big is that? How long is that piece of circle? Okay, the first thing you're going to have to do is convert degrees to radians, because that formula, S equals R theta, is a radian formula. So let's do the conversion. 240 degrees, multiply by the conversion factor pi over 180, and then the word degree cancels, and you're left with, well, 240 over 180 is 24 over 18, or 4/3 pi. And there's a pi in there, so 240 degrees equals 4 pi over 3 radians. And now we use the formula. It's pretty simple. S is R theta. R is 4, theta is 4 pi over 3. We get the final answer of 16 pi over 3. And with a calculator, that's about 16.76 inches. So that's how long that piece of circle is. If you had a string around that circumference, that string would measure 16.76 inches. Now, I mentioned there were two kinds of measurements of degrees and radians, two kinds of ways of measuring angles. There's actually a third method. This is not used that much, but I thought I'd mention it, and maybe we'll do a quick application of it, because it's kind of it's a common way of measuring degrees in some disciplines, and it's called minutes and seconds. And a 1 minute is defined to be 1/60, or 1/60th of a degree, and 1 second is defined to be 1/3600th of a degree. So it's kind of a strange way to measure angles, but it's commonly used in certain areas of science. Let's do a quick conversion so we're more comfortable with this strange idea. Suppose somebody tells you that an angle measures 4 degrees, 2 minutes, 33 seconds. And the symbol for that is the minutes are a single little apostrophe or dash, and 33 has 2 little symbols there. So 4 degrees, 2 minutes, 33 seconds. How many degrees is that? Well, it's not hard to do because you can convert the minutes to degrees by saying, oh, it's 2/60. And you can convert the seconds to degrees because that's 33/3600. And then you add up those numbers and you get 4.0425 degrees. Okay, so converting this obscure technique or this obscure way of measuring angles back to degrees is not so hard. Let's do a quick application of this. Kind of a fun application. It turns out that Erie, Pennsylvania, where my co-author lives in some of my textbooks, by the way, is due north of Miami, Florida. I don't live in Miami. I live north of Miami, but I've been to Miami, of course. Due north meaning they're on the same meridian or the same longitudinal line. And let's assume Earth is a sphere of radius 4,000 miles. That's not quite accurate, but let's assume it is for this example. And it turns out the latitude of Miami is 25 degrees, 46 minutes, 32 seconds north, north meaning above the equator. And Erie is 42 degrees, 7 minutes, 33 seconds. And that's the normal way they describe longitudes and latitudes with this funny measurement. How far apart are these two cities? If you were going to drive from Miami to Erie, how many miles is it? Well, let's figure it out. Let's first convert each of these measurements to degrees. And you do it the same way we did before. 42 degrees plus 7 minutes plus 33 seconds turns out to be 42 degrees 0.1258 approximately. That's how many degrees it is. And the other conversion is about 25.7756 degrees doing that conversion. So that's the degree measure of the angles that these cities make with the center of the Earth. What's the difference between the angles? Well, you subtract them. And if you subtract these two angles, you get about 16.3502 degrees. So that's the degree difference between Erie and Miami if you have the angle starting at the center of the Earth and going out to those two cities. We're in degree measure. We have to convert that to radians, don't we? And trust me, when you do the conversion, you get approximately, again, 0.2854 radians. And now we're almost done. How far is the distance? Well, that's the arc length. That's the length of the piece of the sphere. It's r times theta. R, we're assuming, is 4,000. Theta is 0.2854 radians. It comes out to be about 1,142 miles. That's how long it would take to drive. That's the distance you would drive along the highway if there were a direct route from Miami to Erie. All right, that was a pretty easy application. Let me now, in the final topics here today, studying angles, talk about two topics that are closely related. One of them is called linear speed, and the other is called angular speed. So consider a particle moving along a circular arc of radius r. What is its linear speed? What do we mean by that? Well, if it travels a certain length of arc in time t, then, and it's going at a constant speed, then that arc length divided by time S over t is defined to be the linear speed. Linear speed is basically if you were driving along the circle in a car, that's what your speedometer would show, the linear speed. But while you're driving along that arc, the angle that you make with the origin is also changing. The angle is changing, isn't it? And the rate of change of that angle is called the angular speed. So if theta is the angle corresponding to the arc length s, then the angular speed is the change in the central angle divided by time, theta over t. So in a word, linear speed measures how fast a particle moves. Angular speed measures how fast the angle changes. Okay. Let's do an application of this. Kind of a neat application. I think you'll like this one. And it's a little complicated. Suppose you have an automobile tire, and let's assume that it's a 15-inch diameter. And by the way, this is kind of a trick question because it's a 15-inch diameter, but in the formulas, we're going to want the radius. So the radius is 15 divided by 2. This is typical of trick problems where they give a dimension, but it's not quite the dimension you wanted. We don't want the diameter, we want the radius. So it's a 15-inch diameter, and suppose it makes 9.3 revolutions per second. So every second it goes around 9.3 times. Let's find two things, the angular speed of the tire, and then we'll find the speed of the car. How fast is the car moving? By the way, this is probably, in very simple terms, how speedometers work. So let's do it. Let's do the first problem. So keep in mind that a full revolution is 2 pi radians. A full revolution is 2 pi radians. So if you go 9.3 revolutions per second, and there are 2 pi radians per revolution, notice how the word revolution cancels here, and you're left with 9.3 times 2 pi radians per second. And that is precisely the angular speed. It's 18.6, because 2 times 9.3 is 18.6 pi radians per second. So that's the angular speed. In other words, the angle is changing at a rate of 18.6 pi radians per second. On to the second problem. What's the linear speed? What's the speedometer show on the edge of the tire? Okay, well, linear speed is s over t, the change in distance s divided by time, but s is r theta. Remember our formula, s equals r theta? And theta over t, if I factor the t out, factor the r out, I get r times theta over t. And we just calculated theta over t. That was the angular speed. So it's r times the angular speed. Now here's that trick question. Remember, we need r, and r is 15 divided by 2. The diameter divided by 2. So 15 over 2 times 18.6 pi, multiply that out with your calculator, and you get approximately 438.25 inches per second. Now that's kind of to me, that's kind of a meaningless answer, because I'm not used to talking about cars going inches per second. That's kind of weird. So I converted this to miles per hour. And that took a little bit of work, but it's not hard to do. And if you convert it to miles per hour, it turns out to be about 24.9 miles per hour. That's how fast the car's moving. Isn't that cool? Great application, I thought. Okay. What are we going to do next time? What's going to happen next lecture? Well, I'm excited about it because next lecture we will define the trigonometric functions. I've been waiting a long time to do this, I think. There are going to be 6 of them, and they're built into your calculators. So these are not obscure functions. These are functions that occur all over applied mathematics, science, and engineering. And we're going to define them sort of a classical way using a triangle definition. And then after afterwards, we'll do another way of defining the trigonometric functions, but we'll, of course, get the same answers. So I'm really looking forward to our next lecture because we'll be truly diving in to the subject of trigonometry. Thank you very much.